Hello, and welcome to the SMR control tutorial with BCI2000. SMR stands for sensory motor rhythm. Before talking about the control experiment, we will first walk through some key concepts of SMR. In the human brain, the primary sensory and motor cortices are located along the central sulcus, crossing symmetrically from the left to the right hemisphere. Looking at the motor homunculus, right hemisphere, each area on the cortical strip is devoted to a certain part of the left side of his body. For example, with EEG electrodes CZ and C4, we can capture the neural activities from the feet and the left hand. In human EEG, primary sensory or motor cortical areas typically exhibit rhythmic activity at a frequency of approximately 8 to 12 Hz when they are not processing sensory information or producing motor output. If the subject moves his or her left hand, we can expect to see a reduction in sensory motor rhythm power around channel C4. We can then associate that reduction with a desired task, such as moving a cursor on a screen. In our experiment, we will first collect the subject's sensory motor rhythm through a calibration session using EEG. Next, we will analyze the EEG recordings and extract the subject-specific SMR features. We will then conduct a BCI control experiment using the selected feature. Before starting the calibration, let's look at the hardware and software needed for our experiment. Preparation. To conduct an SMR expeller experiment, we use the following materials: electroconductive EEG gel, paper towels, syringe heads, syringes, alcohol pads, wood cotton sticks, a measuring tape, an EEG cap with 8 passive channels, and 2 soft squeeze balls. The hardware includes a Windows 10 laptop, 2 monitors with 1080p resolution, and a biosignal amplifier. This amplifier is a G-Tech G-USB amp. Recorded signals are sampled at 256 Hz and a 24-bit resolution. The software in this experiment includes BCI2000 and MATLAB 2016B. To determine the size of the EEG cap needed, we measured the largest circumference of the subject's head. The reading is 59 centimeters. The medium cap is appropriate for 56 to 60 centimeters, so this is the cap we will use. On our EEG cap, there is 1 electrode behind each ear, one for the ground and the other for the reference channel. To ensure optimal conductivity, we clean behind the subject's ears with alcohol pads. Now we can put the cap on the subject. To detect the sensory motor rhythm, the montage of our EEG cap has channel C3, CZ, and C4 that cover the primary motor and sensory cortices. To ensure the alignment between the electrodes and the cortex, we need the channel CZ to be halfway between the nasion and the inion. With a measuring tape, we first identify the location of the nasion, place the measuring tape, and find the reading at the inion, which is about 41 centimeters. We then locate CZ and ensure that it is at about 20.5 centimeters from the nasion. Adjust the cap if CZ is not 20.5 centimeters from the nasion. Once the cap is aligned correctly, we can close the chin strap. Now let's get to the computer and open the BCI2000 folder. Inside the batch folder of BCI2000, double-click a stimulus presentation file with your amplifier's name. After entering config, load the parameter SMR screening left versus right from the parameters folder and enter your name. We then load a display parameter that tells BCI2000 the resolution of our monitors. Following that, we can switch to the Source tab. Select Impedance Measurement in the Acquisition mode. Scroll down in the Source tab and disable both the bandpass and notch filters. Close the window and click Set Config. The impedance window will open. Our desired impedance is to be below 30 kiloohms. As shown in the window, since no gel has been injected, our impedance is at the magnitude of 10 to the 5th kiloohms for all channels, indicating that there's almost no conduction between the cap and the subject. To fix this problem, we will now inject gel into each electrode. With the syringe prepared, it is important that we fill in the gel before putting on the needle tip. After squeezing out air bubbles, we can carefully inject gel into the opening of each electrode. Only about 1 milliliter is needed to bridge a contact between the scalp and the electrode's recording contact. Also, be sure to apply gel at the appropriate ground and reference sites. The mastoid process behind the ear and the forehead are commonly used. After the injection of gel, we can click Set Config again and see the impedance between each electrode and the skin underneath. The impedance of all channels is greatly reduced. F3, T7, and T8, however, still exhibit values larger than 30 kiloohms. To improve our impedance values, we will first abrade the skin underneath those channels with the tail of the cotton stick. We then reapply gel to those electrodes with impedance above 30 kiloohms. Sometimes it takes several rounds of this procedure to achieve a low impedance value. Now that we have all impedances below 30 kiloohms, we can inspect the quality of the EEG signals. By turning off both the low pass and notch filters and setting the high pass filter to 0.1 Hz, we have revealed the noise induced by the 60 Hz utility frequency. As this noise might diminish the quality of the raw signal, we can eliminate it by grounding the subject to the amplifier. By placing a hand on the outer metal casing of the amplifier, we can see a significant reduction of the line noise. As a final step, we will test if the subject can produce some physiological artifacts. Now we ask the subject to clench their teeth to produce a muscle artifact, close their eyes to increase their alpha band power, and move their eyes left and right to induce an EOG artifact. The subject should try to avoid any of these movements during the EEG recording. Calibration experiment. Before the session starts, the experimenter should explain the expectations of this session. The experimenter should ensure a quiet environment and prevent any source of distraction to the subject. The subject, in turn, should avoid muscle movements during the session. In the calibration session, the subject will move their hands according to the stimulus cue. For our experiment, the subject is expected to squeeze the ball with his left or right hand based on the cue, and avoid movements during the baseline periods. It is recommended to collect 20 minutes of data. Let's now get back to BCI2000 and click Config. In the Source tab, enable both the bandpass and notch filters. Next, scroll up to the top and switch the acquisition mode back to analog signal acquisition. Before starting the experiment, it is important to know how to control the duration of each session. In the Application tab, scroll down to the Sequencing section. There are two key parameters here. The first one is the stimulus duration, and which we will set to 3 seconds per stimuli. The second is the min and max interstimulus interval duration, which we will set to 3 seconds between each stimulus. A sequence here is defined by the enabled tasks and their respective rest periods. In our experiment, the first 2 stimuli, left and right hand, are enabled. With 2 enabled stimuli being presented for 3 seconds each in a randomized fashion, a single sequence will last 12 seconds. Our goal is to collect 20 minutes of training data. However, we will break up our session into 5-minute blocks to limit subject fatigue. With 12 seconds per sequence, we will set the number of sequences to 25 for a 5-minute recording session. Between each session, we will give the subject a 1-minute break. Now we can close the window, click Set Config, and wait for the signals to stabilize. Click Start. During the session, the monitor shows either the left hand or the right hand. The subject squeezes his corresponding hand. When the cue disappears, he returns to a neutral position. When the session is finished, a cue with the word timeout will be shown, and BCI2000 will pause. During this time, the subject is free to take a break. Offline analysis and feature selection. After the first session, we are interested in the quality of the data. In the BCI2000 folder, we open the Offline Analysis folder in Tools and select the Offline Analysis batch file. Note that the Offline Analysis toolbox operates with MATLAB, and the computer in this experiment has MATLAB 2016b installed. Choose Frequency in the Analysis domain and EEG in the Acquisition type. Click Add to import the calibration data from our first session. In target conditions, enter left hand and right hand for the labels 1 and 2. Make sure that in Spatial Filter, Common Average Reference is selected, and click Generate Plots. After a few seconds, a feature plot from the subject will open. The color codes represent R-squared values that vary between 0 and 1. In the context of our experiment, a high R-squared value, shown in red, represents a major influence of that specific region of the brain at a specific frequency on the task. We are particularly interested in the cortical activity located around CZ, C3, and C4, around 8 to 12 Hz, as these activations are associated with motor movement. In channel C4, we find a peak at around 5 Hz. We can explore its spatial information by filling in spectra channels and topo frequencies in the Offline Analysis tool. Click Generate Plots. As there's no red color around CZ, C3, or C4 at 5 Hz, we can try some surrounding frequencies. From the topography of 6 Hz, we still can't see a clear representation of SMR activity. Therefore, we will collect more data with more calibration experiments. When the subject is ready, click Resume to start another 5-minute session. After collecting a sufficient amount of experiment data, we will proceed to the offline analysis toolbox. Preset the toolbox like the previous steps. Add more calibration experiment data into data files according to the amount of data collected. This time, we will look at the SMR of each hand separately. In target conditions, change condition 2 to 0. This allows us to directly compare the brain response of left hand stimuli versus rest. Click Generate Plots. From the feature graph, we can see that for this subject, when moving the left hand, both C3 and C4, or his right and left hemisphere, were active. Now if we want to see the spatial spectral information of those peaks, we can read them off the feature graph and enter the frequency and channel information into the toolbox. As shown in the topograph, both regions were activated during the left-hand movement. While the peak happens to be at 11 and 22 Hz, we will only use the first peak for SMR control. Let's now change the target conditions again. If we look at the right-hand stimuli versus rest, we see there is some activity still on the right hemisphere, but most of the activity is concentrated on the left hemisphere. Like the concept we introduced in the beginning of the tutorial, the spectra C3 graph to the left gives us very good spectral focus of SMR, while the topography gives us the spatial focus. The R-squared value at C3 of 0.27 at the first peak is good for BCI control. Therefore, for our subject, his right-hand SMR activity can be found at 11 Hz on channel C3. With this information, we can close the stimulus presentation window and open the cursor task batch file for BCI control. Click Config and load the SMR basket task parameter file located in the Parameters folder. In the Storage tab, enter the subject's name. In the Filtering tab, find Spatial Filter and click Edit. In the Spatial Filter matrix, there are 3 rows that consist of different contributions from all other channels. Channel C3 is at the first row. With this in mind, we can go down to Classifier and click Edit. Type 1 into Input Channel and 11 Hz as the input element. No change is needed for the other 2 numbers. Click Set Config, and when the signal stabilizes, start the initial session. Ideally, the initial session is conducted in a quiet environment. During the experiment, avoid any moving object in front of the subject. For the subject, when the red target bar is at the top of the box, stay motionless as if there's no stimuli given. When the target is given at the bottom of the box, squeeze the right hand as if there is a right hand cue given. It is important to know that during the initial session, the ball might not follow the subject's intention. The initial session should last about 2 to 3 minutes. As the subject is reacting to the target, the program adjusts its linear classification parameters. As the initial session ends, we can now proceed to our final section, the BCI control experiment. Brain-computer interface control experiment. In the BCI2000 operator, click Config and find Adaptation in the Filtering tab. Of the 2 numbers in Adaptation, the first number controls the horizontal component of the ball, and the second controls the vertical component. Here we will change the number from 2 to 0 as we have finished the adaptation of the linear classifier. Just above that, in Normalizer Gains, we will increase the number by 1 so that the ball will be more sensitive to the change of the SMR. After the changes, we can close the window, click Set Config, and start the BCI control experiment when the signal stabilizes. During the experiment, it might take several trials for the subject to become familiar with controlling the ball. Furthermore, studies suggest that imagined movement can also achieve BCI control with similar features of SMR. To test that, we asked the subject to apply the same guideline with imagined right hand movements. Although the result has less accuracy, by practicing and improving the parameter, BCI control can be achieved without physical movement. More information about SMR control and BCI2000 is available on our wiki page. Thank you for watching our video.